It's too loud. Hello, everyone. Thank you for joining today's AIAA Los Angeles section e-town hall meeting. We have a very exciting topic today. Everybody got very excited, and we have a award-winning speaker coming today. Yeah. So, and first of all, we thank the Hudson Library. Well, we should for offering this nice facility, but hopefully more people show up in person, not just stay home. Yeah, for folks, if you live nearby, please come here, join us. Don't just stay home. Um, okay, so before we start the program today, I'll just mention some logistic for folks here. The restroom you can see here, right here. You can use the restroom. There's another one outside, but outside you have to wave to the librarian. And then we have some donut on the back. Welcome to enjoy it. So we have the meeting room until 2 p.m. So welcome to with the speaker whenever you with us whenever you have to leave. So on the other hand, if you are not yet a member, please consider joining AIAA. AIAA really give you a lot of benefit. Like me and Jimmy, the AIAA member, and there's a great benefit. Uh, so and you enjoy a discount to conferences and a lot of career and other possibilities. So I don't want to talk too much today, but just let you know what we are doing because Los Angeles, a lot of booming industry, spacecraft, AI, a lot of company doing, those things. 2 weeks ago, we had a visit to Impulse Space. They got a contract from DoD, Space Force, and there's a reconnaissance office, national NRO, and they team up with some company doing AI. So I've been telling this is a great event. Um, so, but at the same time, we also work with industry. So once in a while, we have exhibitor. If a larger event, we have more exhibitor. For individual speaker, then we generally invite one exhibitor one at a time. Last week we have speaker from JPL. Then we have a company exhibitor. So today we have the great pleasure to have booming industry, not just providing hardware, software for CubeSat, but other very exciting products, including education. So we have the president of the Gran system. He's going to tell us what he about himself and his company. So, Mr. Kirk, go ahead. Oh, yeah, okay.
Hello, can you hear me?
Yeah, yeah.
Hi,
Yes, I can.
this is Guanghan from Gran Systems, and we are a company of 16-year-old, and we are working on a few segment of the industry, and we are in the new space industry and also the semiconductor industry. Um Right now, we have produced more than 100 CubeSat subsystems, and so we are a mass production house with a production facility in-house. And we also help companies uh, do contract manufacturing for mass-produced space components and systems. We have supported 46 space missions, mostly about 80% from academia. Uh, we supported many CubeSat teams to provide hardware and some software and the mission management. And we currently do aggregate some launch capabilities using the SpaceX rideshare program, and we have a contract conducting lunar lander payload mission, to put an a small observatory on the lunar lander to land on the moon, and we have had several events that we organize or co-organize for space education, mostly in Taiwan and Southeast Asia and Latin America. So that's a brief introduction, and I we are currently setting up our office in Houston area in Texas. Hopefully, we will join some of the industry ecosystem in Southern California in the future. Okay, thank you.
You, Guanghan, Mr. Ke. This is really amazing. Hopefully, you can join us here, the ecosystem, pretty soon. Then we'll also hear from you about later on for more about more detail. And actually, Mr. Kern is also expert in some other things, and so we will gradually learn more from him. But if you are interested in his in himself and also in this product company, they have a website, Gran System. You can take a look. We'll post it on the website as well. Okay, so we'll move on to today's main presentation. Well, as you know, this AI has been, gradually gained very huge attention in the space industries. So you have the company like Andrew and many companies. And I was there in AIAA Ascend last year, and they were just so big. All the main topic was AI on spacecraft, and also there was an aviation conference. Everything is AI these days. But AI. You talk about AI, those kinds of things, machine learning. But the most important thing is the people behind developing those important algorithm and study. The important thing, like our speaker talked about the safety, collision avoidance, those kinds of things. And so Jimmy is a PhD candidate. Is about to graduate. He is doing wonderful work with the advisor, Professor Sunjong Chang, who spoke with us 3 years ago, and immediately got attention worldwide and got a visit from our AIAA CEO, Dan Dumbacher, to the Caltech laboratory, and with Jimmy, and also even important people from Japan, international, celebrity. And it's a very important topic. And Jimmy actually won the AIAA Best Paper Award last year, and he presented in 2003 AIAA SciTech, 2003 or 2004? 23. So, we actually got this late, so we kind of celebrate a little bit today, but so congratulations, Jimmy. Yeah, so this is one thing that's good for AIAA, encourage people to develop. So Jimmy is going to tell us more about the story, how they developed this, safe active fault estimation for spacecraft. And as you know, in their lab, they actually also develop things for, formation flying. So he's in their Caltech space engineering group, and they actually do a lot of things in like autonomous response and also like a deep space proximity operations and detecting cyber attacks, information flyings. And he got his bachelor degree in aerospace engineering and as well as astronomy and physics from University of Washington. This is the best combination. Many of our leaders in industry, they have astrophysics, physics, and they got a little bit aerospace engineering. That's the best. So let's welcome Jimmy for today's presentation. Thank you.
Thank you. That's very flattering. Hope I live up to the expectations. Before I start, just want to say hi to everyone. Thank you for coming out on a Saturday. For the online folks, if you at any point or can't hear me or something coming through on your end, raise your hand in the webinar and I'll rely on Ken to let me know so I can go back or make sure you get the full value of the presentation. Also, this is, I think, about normally 45 minutes to an hour on presentation. So if you have questions about things that aren't clear or clarity,
AC, you raised hand. Do you want to say something?
Yeah, there doesn't seem to be any video coming through on the Zoom.
Video.
Did you share the chart?
No,
You see,
Can you see the chart?
no, there's no slides or uh, there's only the sign that says Save Active Fault Estimation for Spacecraft, and
yes,
and so is that what you're referring to?
that's the correct slides.
Oh,
And
okay.
then there should be a presenter video, but I think that's one of the AIAA panelists. You might have to. I don't think it's the same one as the one that's talking.
Oh, okay. Well, the other panel is just a kind of
No,
a
AC, this you can adjust this on your screen.
Yeah, you should be able to adjust the video window on your own screen. It should be the camera panelist.
all right, and it doesn't seem to show. It alternates between a picture of like the moon or something, and then AIAA text.
No,
But it
this
doesn't.
is you can adjust the view. Go to upper right on your screen. You can adjust the view.
Yeah, you can pick like side by side with content is probably going to be the best one. Unfortunately, I can't demonstrate that.
Yeah, we cannot adjust it for you.
Well,
It's on your end.
I see it, and I'm clicking on it, and I still don't have a video, but I can hear. So maybe I don't seem to be. I am at the upper right hand corner where it
But
says side by
let me
side.
ask. Okay, AC, let me ask the other audience.
Sure.
Kartik,
Okay. Fine.
Kartik, can you see the presentation, Kartik?
Yes. So on the main screen, I see a slide saying Safe Active Fault Estimation for Spacecraft by Jimmy
Perfect.
Ragan.
Okay, so since Kartik can see it, that means AC, please adjust your
Well, no,
the view.
I see that also, but I just don't see the I don't see the presentation video. So I can't see if you have a video of the room or of the speaker. I don't see that, but I do see the slide picture.
Interesting.
Sorry,
Okay.
that's what
I
I meant.
Do you
Try to-
have video of the room? Because I don't see video of the room either.
Weird.
That's what I was referring to. There's no video of a speaker.
Oh,
or the
you are
room.
not saying the slide.
Oh,
you are
now
saying
I
the
see.
video.
Now I see another slide that says overview.
There's another slide. Oh, I see the camera video. One trick you can do is if you see the blank
Oh,
boxes.
now I see it. It just now came on.
Weird.
All right,
ju-
all right.
It just
Let's
now came
proceed.
on. Okay. All right.
Okay.
Thank you.
Sorry for this. Yeah.
That's
No
unfortunate.
problem.
So
Thank you. Thank you very much.
appreciate for speaking up. So yeah, as I was saying, if there is any technical issues, please let us know because otherwise I can't tell. But
It's great now.
uh,
Thank you.
great. And if there's any questions or things that aren't clear, feel free to interrupt. Otherwise, I'll have breaks throughout for slightly bigger questions. And at the end, I think we have about 15, 20 minutes set aside for Q&A. So let's get right into it. Safe fault estimation for spacecraft. It's kind of an umbrella topic of a few pieces of work that I've been doing throughout my PhD. So let's start with a motivating example, which is what you're seeing on screen now. We have some spacecraft and it's approaching an obstacle. That could be another spaceship it's docking with, some bigger space station. Maybe it's a asteroid or comet it's trying to land on. That's all well and good, but unknown to the spacecraft, it's two retro thrusters that it needs to use to slow down. This is the bigger visualization of the components. Spacecraft's right here in physical space are broken, but it has this belief over what it thinks is the health status of each of the components, and currently it's none the wiser. This is a problem because it needs to slow down very shortly, and if it waits to fire its thrusters until the optimal time for landing, it's going to be unpleasantly surprised to find that it's not slowing and it is instead crashing into the rock. Our method will proactively test each of these components and will find out before it becomes too late that something is going wrong and that it needs to dodge to the side to get itself a bit more time to diagnose, reorient, slow down, and resume a stable motion. I'll go into how we develop the algorithm, how this works, what's going on here later throughout the talk. But I want to start with some context on fault estimation and kind of what our motivating reasons for doing this work was. So if we look on this example here, traditional fault estimation typically involves a process of where you have some sort of signal that you're monitoring. And if it goes above a threshold, you trigger an alarm because that indicates you're out of spec, you're out of tolerance, and you determine that based on knowledge of your system, of the noise, of what you expect to see versus what you don't expect to see. And you can get some very creative monitors and residuals here to cover a wide range of system behavior that you might be worried about. For example, you could have some sort of model where you have multiple different fault models that you could be switching between, each of these signals is indicating, and maybe some catch-all unknown when multiple combinations of residuals go off that you weren't expecting. You could have a model of the input-output consistency of your system and have that for every component in some sort of digital twin or other method of mapping the system, and go, okay, does the forward pass from the inputs to this component match the backward pass from the outputs that we're measuring throughout the system? And that works pretty well. That can give you a really good insight to when faults are occurring, but there are some challenges with this representation. And the main question we're asking is, what happens when there's ambiguity and multiple possible fault scenarios can explain what we're measuring? So I come from a controls side, so and particularly partial observable control. So I like to think about things in terms of belief distribution. So you'll see a lot of like Gaussians throughout this talk, kind of representing the idea of the information we have. So if there's a lot of overlap between these two beliefs that could correspond to different faults, we might not have good insight onto what the root cause of the problem is in our system and what we should do about it. And traditional fault estimation doesn't provide a way to resolve this. So the question might be, how can we get more information so we're not just waiting for something bad to happen to us to get to discover what's actually wrong with the system? Can we be proactive about this? And there's a body of work that's been done in the last like decade or two called active fault estimation, which just seeks to do this directly. It seeks to proactively gather information about the fault state, and the visualization I like to use is trying to spread these two Gaussians apart, reduce the overlap in plausible scenarios, so you're more likely to have discriminating measurements, so that there's only a few different measurements that would be explained by multiple things. It's an optimization problem if that's the case. And this works pretty well, but there are limitations that existed in published literature and work that had been done before. Namely, they might be limited by the range of systems they apply to. Some of the most powerful work is limited to, say, linear systems or only specific classes of faults. And they may not work very well in real-time situations. So you might have to do either heavy offline computation beforehand, which maybe isn't flexible if something changed on the approximations, or lose some of your theoretical guarantee to run on online, which is something we want to do if we're going to do safety of the system. If they're taking actions to gather information, you have to ask, well, what if we take an action that's, for example, sends our spacecraft into that asteroid we're trying to avoid? The work we published this summer called Online Tree-Based Planning for Active Spacecraft Faults Estimation and Collision Avoidance. It came out in Science Robotics in the August issue. So if you're interested in looking into this in more detail, I'd direct you to there. You can also contact me. I'm happy to send you the copy. So before I go further, I want to outline how the rest of this talk is going to go. So first, I'll go into the problem formulation, make some of these ideas a little bit more concrete. And then I'll go into the algorithm that this paper covers, which is what we call SFEAST, or Safe Fault Estimation via Active Sensing Tree Search. And I'll explain what each of those components means, as well as by first introducing the algorithm without the safety, and then talking about how we added in safety constraints and kept our theoretical guarantees. I'll go through some of our simulation validation and hardware experiments, and that'll make the bulk of this talk. And then the last like 15, 20 minutes, I'll go into some extensions that we've done in some more recent work and like other systems we can apply this to beyond either spacecraft or beyond with failures. So let's dive into it. Problem formulation. So I've alluded a lot to this idea of trying to do active fault estimation. What do I mean by this, and why do we need this? So the main mode guiding questions are, can we improve model-based fault detection with planning? So if we are aware, is something not working? Oh, yeah, I've been avoiding it so that online can see as well. Okay, where did everything go? Okay. Do you know where that feedback's coming from? Did I unmute somehow? There should be a mute button at the top. Oh, perfect. I think you hit it. Appreciate it. Otherwise, I hear my speaking and no worries, no worries. Where was I? Oh yeah, so we're trying to improve on this idea of model-based fault detection with planning. So this flow chart we have on the right here is illustrating our high-level ideas. We have some planner. It's going to take an action on the real system, and we can identify differences between what we expected to see in our simulation, our simulated observations versus what we actually see from the physical system. And that should give us some insight to update our belief state of the system, what faults occur, things like that. And we can iterate and loop and try to like build, we can try to plan actions that will make this information update as useful as possible. And we're hoping that by doing this, we can combat uncertainty that comes from noise or system complexity, redundancies, and things like that. And the ultimate vision is we're trying to move towards a direction where we can autonomously take care of this uncertainty without needing to go mode, without needing to rely on the ground. Because if we want to do missions that are in deep space or have fast time horizons, this is going to be necessary. We can't wait to figure things out. We can't just like go back to the engineering model and tinker with it if you're going to crash in a couple of minutes. This is, we think, enabling technology for true in-space autonomy. So to put some math to it, we start with, at the simplest level, a linear system with actuation and sensing degradation and bias. So what do I mean by that? So we've got a lot of equations, but they're not saying anything too complicated. We have the same system with linear control input, maybe potentially nonlinear dynamics. And we have this matrix here, which is representing how degraded our actuators are. So if this matrix is a diagonal matrix with zeros or ones on each element, if it's 0, nothing's happened. If it's 1, the actuator is totally degraded. It doesn't do anything anymore. But to capture the case where something might be stuck on, we also have a bias matrix, which is again diagonal matrix with zeros and ones. If it's a 0, there's no bias. If it's a 1, something is putting an input in uncommanded and constant into the system. We then have process noise as well, because we're interested in being able to do this even when the system is noisy. And then the similar type of thing for the sensors, where we again have degradation and bias. So each of these, we have 4 different sources of failures that can come in. They each stack up into a large failure vector. And we can combine that with the state space, the state vector, to create this idea of a composite vector on both states and failures. And then because this is just an augmented state vector, we can perform statistical inference on it, do a Bayesian update, just like before. The challenge is that this update might be hard to write down a closed form or solution that's also computationally tractable. So that represents a potential challenge with this framework, and we'll get into how we solve that later. But the idea is we're just going to use the information we already have, update with our measurements, and iterate. This allows us then to define a reward on what we're trying to do. We're trying to gather information about the underlying fault. So that's what that's on the left hand of the equation 7 there is we're saying we want to maximize how confident we are in the underlying fault. And by squaring the belief over the reward, we do that, because when we have equal information about all possible faults we're considering, this will be spread out distribution. When you square it and sum it, you'll get something close to 0. When we have exactly one possibility we're sure of, this will be exactly 1. So it's monotonically increasing as we have more confidence in our belief. And on the right, I'm just showing that we get to this defined belief over failures by just integrating over all the state space. So we're doing a marginalization. All this allows us to define what we're calling our active fault estimation problem. So what is this? It's the idea that we want to plan actions over a horizon up to time length capital K that will maximize this reward. So we're, again, trying to gather information about what's going on with the fault space in particular. That's what the reward is on. Not on, we don't care where we are in physical space. We just want to maximize fault. We'll get into constraints on the physical space when we think about safety later. So this is a lot to say that we want to maximize some value out of our control policy, which is represented by that pi. So we can kind of hide that all away and say we're maximizing the information gathering value. And that's what we'll be doing throughout as I develop the theory further. But there's a challenge here because we've written it all down, and if we'd solved it on the first slide, things would be great. But we don't have a closed form solution to this. Like a lot of optimal control problems, it can be intractable once we start factoring in things like uncertain information, this reward that's a little bit complex, maybe non-convex constraints. So we can't just go ahead and solve this. So what we're going to do instead is we're going to, in our development of the feast algorithm, we're going to come up with an approximate way to solve this that'll converge to an optimal solution. That's what we're going to be looking for. So one way to do this is to reformulate it as a observable Markov decision process, often called a POMDP. The diagram on the right is showing what's going on here. And it looks kind of messy, but it's actually not too complicated of an idea. We're just going to think of this optimal control problem in terms of a sequential decision-making problem. So we start on the left at state 0, and we can't directly see this state because we don't have full observability. We have partial observability. So instead, we have a belief that refers to our current knowledge of what the true state is, and we could define a reward on that, which is because we want these beliefs to be as informative as possible. Given this belief, we can decide on an action we want to take. That action will propagate our state in some sort of stochastic manner due to the noise in the system and our uncertainty of what the true state is, to a new state, S1, and we'll also get an observation from that new state, which again is noisy. That allows us to update our belief using knowledge of both the action we took and the observation we've gotten. And we represent these as maps. That's T is the map from the old state to the new state given an action, and Z is the map from the old state to a new observation given an action. So we can represent this all mathematical machinery, and we can translate the equations we had on the previous slide to fit into these notations pretty compactly, or pretty directly. It's obviously not compact. It looks like a lot of math, but all I'm saying is that these transitions were given to us by the dynamics, so there's nothing fancy here. And this is a lot of hand waving into an equivalent reformulation, and we can prove directly that these two are, that what I had on the previous slide and what I have here are the same problem. So you might go, why did we put all this math down? What's the point of this? The point is that POMDPs have a lot of algorithms that can be applied to them that converge to optimal solutions. And that's something we want because we don't have that with the optimal control formulation. So we can write what we want in optimal control, and then we can rewrite it in a version that's solvable with the POMDPs. And in particular, the algorithm we're going to use is Monte Carlo tree search, which was originally developed in the field of playing games. And in a way, a POMDP is a single player game. The way this works is that we have 4 phases. We select which actions we should do down the tree according to this augmented value function. What this augmented value function is doing is it's balancing what we know works well in the past. We call that exploiting information with what we haven't tried enough to be confident about. We call that exploration. That's what that C term with the log ends is doing. So things that have worked in this diagram, things that have higher value from previous exploration are darker green, whereas things that haven't been explored as much are smaller nodes. We might sometimes prefer to try something that has less value if we haven't tried enough, just to give it another chance. And the context that this theory was developed in actually was with playing slot machines. Whereas if you're at the casino, you want to go back to the machine that's been giving you some payout, but you might want to try the others every now and then just to make sure you're not missing something better. Unlike with going to Vegas and playing at a casino, you can win because we are looking for good things to do here, not ways to spend more money on a one-armed bandit. But you'll hear multi-armed bandit as the origin for this type of theory. The nice thing, though, about using this machinery is that there already exists a convergence rate that we can inherit if we can make our problem match what this Monte Carlo tree search is working on. And that's saying that the optimal the value of the policy we're, if the policy is determined by this tree, converges to the optimal one with that convergence rate shown. But the takeaway for our case is that this exploitation versus exploration trade-off gives us value convergence. And if we have this, we're in a good spot because that means the longer we run this algorithm, the better result we're going to get, and that we can be sure that there is some theoretical guarantee that we're going to be converging to the best actions we should be taking. And again, we're trying to find the best actions we can take to diagnose our fault. So this is really good to have. And this is why I like working with tree search domain as opposed to other types of like artificial intelligence, like neural networks, because they lack this guarantee. They work well in practice, but they don't have good theoretical understanding of how they converge, whereas trees are much more interpretable and they have a theory that we can build off of. So I like to call this type of work AI adjacent because it can be augmented by AI methods, but it has its own interpretability that's usually separate from what you hear with neural networks or like deep AI. Back to our setting, we're actually in the partially observable system, which is a bit more complicated than the fully observable system because, let's see, it's showing up the greatest for people in the room, but I'll highlight things. Bear with me online. We have 2 rounds of branching. I'm just going to go to this diagram, which has better, shows up a bit better on the projection, and then I'll head back. There's 2 rounds of branching per decision we make. So we select an action to take, and that action generates an observation. We can control what action we take, but we can't control the observation we get. So this makes it a little bit harder to plan on because there's extra levels of things that can happen, extra combinations, and extra uncertainty, which has made historically doing tree search in partially observable settings difficult because of this extra level of branching. And there's exists algorithms to solve this, including partially observable Monte Carlo planning, or POMCP, which we extend in this work. And they have a few, these existing methods have a few advantages already in that they retain properties of Monte Carlo tree search, such as this asymptotic convergence to the optimal value, real-time solutions, because we can run this tree as much as we want, pause at any time and get the best answer. And if we have more time, we can just run it longer and get more convergence to that optimal value. So we get better performance with more computation. And the way it's doing this, going to the bigger diagram, is it's using a particle filter to simultaneously estimate the state of the system and the value function of each action. So what they'll do is they'll start at this top, sample a particle from the initial particle filter that they had before they started the tree search, take the selected action to propagate that particle to a prior belief. From there, they can use their onboard model to simulate what an observation might be and use that to simulate this branching of reality based on the observation you get. Take the propagated particle, put it into the next node, and then repeat this process down the tree. So it's a clever algorithm that manages to combine 2 of these key steps. And for most systems, it works pretty well because these particle filters are known to converge the optimal belief with a sufficient number of particles, in this case, sufficient number of simulations. And because of the way they're also estimating the value at the same time, they're also going to converge the optimal value. We have this exploitation versus exploration trade-off, and this is great. But I did say there that this works for most systems. There's a key problem in this area of information gathering. And what that problem is that when your reward is a function of belief, you can't estimate the value very well until the particle filter converges. To see why, I've gone back to our equations where we have this definition of a belief that's the sum of our belief on different faults, our square sum. So when there's only one particle, that sum evaluates to exactly 1, maximum reward, because we're absolutely confident in what the fault is. There's only one possibility at each of these nodes. But we know that's not true. It's just an artifact of not having enough particles to converge to the true belief. So the second we revisit these nodes, the belief is going to drop because we've added another particle into the system, and we're now less confident. So this filter is not giving, or this tree search is not giving us a good representation of what the value is because it has no idea. So it's going to explore in a breadth first manner, which is for tree search, a death sentence, because it means there's no point in doing this. You have to try everything in a brute force approach. That's not good for us. So until this converges, we're going to see, until the particle filter converges, we're going to keep seeing this behavior. So we will converge the particle filter, but we're not getting exploitation versus exploration trade-off until much later down the line. So you're wasting a lot of computational effort just to converge your particle filters. And you have to do that for every area you want to explore in this tree. So there's no way to steer the tree towards areas of high reward, what we want to do. To see what's going on here, we can visualize a bit of what this fault estimation problem needs us to do and why this the particle filter approach just isn't working. So each of these particles in a node of beliefs corresponds to a particular failure and a position in space that the system might be in. If we stack them all up, we get a pretty okay representation of what the failure on the spacecraft might be. But the spatial information is really bad for this number of particles. So we need a very large number of particles to have any good representation of where the spacecraft is. And that means we're losing a lot of efficiency. So instead of doing this brute force trying to edit everything at the same time, can we potentially decouple this failure state and physical state estimation? Can we exploit the problem structure and be a bit more creative about this? And to cut to the chase, we can. That's one of our contributions, is we've come up with this idea we call our marginalized filter, which is to realize that the position of the spacecraft can be conditioned on the underlying failure, because the dynamics of the spacecraft depend on what the fault state is. So if we assume a fault state, we can then propagate just a Kalman filter or extended Kalman filter in the nonlinear case of where the spacecraft is, and we can sum those up to get a much richer representation of the physical state of the spacecraft, while keeping our understanding of what the fault state is. And this is basically the same thing. If you take a bunch of Gaussians, add them up, you can get these kind of complicated looking distributions with less information than you would need to represent that whole distribution. As a whole, you can approximate it quite well. And in the case that this system's linear, this approximation is actually exact. There's no loss of information because the Kalman filters capture everything completely. So the key idea here is that we're exploiting this problem structure to make the marginalized filter get exact belief updates. And this is great because that means the first time we encounter a new node, we can run this filter because we've made this computationally tractable by separating out the parts we need to compute and the parts we don't. Get a full Bayesian update, get a full information about what the reward would be if we took this action and saw this observation the first time we visit a node, as opposed to needing to visit it like dozens or maybe hundreds of times to have that information, which means that we've now recovered this exploitation versus exploration trade-off that we were looking for. And we can now, again, steer the tree towards areas of high reward. So putting that all together on like our simulation spacecraft, we've got this tree that's now exploring. It'll take an action, get some more information. It can then simulate like a potential future, such as going down one branch of the tree, thinking about the information it might get if it were to play out that tree. And after it's done that, all right, we're back. After it's done that number of times, hundreds, maybe 1,000 times if you have enough simulation, it could select what the best action is that historically leads to good information. That's what we're trying to do, is we're trying to find the action that should give us the most information, and the most information over a horizon, not just the next time step. And we can do that and explore around the tree, continuing to gather information, even in a highly noisy system, until we eventually converge to the true underlying fault. So this is great. And this is where we were when we did the AIAA paper that Ken was talking about at the beginning. But an obvious question that you might ask is, if we're injecting actions into the system, kind of shaking things out to see what hurts, if you will, what happens if that action is unsafe or maybe damaging to the system? For example, if we start on a collision course with this little comet, taking these actions to diagnose, we found that the thrusters are broken pretty quickly, but we've hit the comet and we are now dead. It doesn't matter if we know what the fault is if the spacecraft breaks. So can we revisit this and add safety constraints and still retain this gathering of information, but can we add a safety filter in so that we are also taking actions that not only we expect to give us a lot of information about the system, but we also expect to keep us safe with the information we already have. So, which is basically what these motivating questions are. And to cut to the chase, yes, we will, but here's how we develop it. So the main idea we have to like formalize this concept is we want to define a set of safe beliefs and then ask that our planner keeps us in this set of safe beliefs, if at all possible. The reason why we have to do a set of safe beliefs and not a set of safe states is because we're partially observable. We can't know for sure where the spacecraft is, but we can define an understanding of how likely we are to be safe. So we'll start with the set of safe states, and we'll define that in terms of some functions that need to be greater than 0 to ensure safety. You can think of this as an inequality: be on one side of the wall, not the other, or one side of the obstacle, not the other. We can combine multiple of those if we want to have a complex set of obstacles, maybe something non-convex, what have you, and define the set of safe states as the X's, which satisfy all of these safety constraints. We can then say the set of alpha safe beliefs given this set of safety constraints is the beliefs such that the probability of being inside the safe set, is at least alpha. Being more confident we're safe than alpha is fine, but we want to be at least alpha. And visualized on the right here is kind of what we're talking about. Is these ones far away from the obstacle, there's no chance of collision. They're inside this set, this safe alpha set. This one here is a little too close to the obstacle for the amount of uncertainty we have. If we were very confident we weren't inside the obstacle, it'd be okay, but we're not. We have this overlap here. So this actually goes into our unsafe set. So we would like to demand that the planner stays outside of that unsafe set. And so we'll add a constraint to our problem. We'll say the safe active fault estimation problem is to do this, this maximization we had before, subject to this constraint. Well, this is great. I jumped ahead. This is great, but the problem is that applying this constraint directly in the tree search is going to break our theoretical guarantees. It doesn't match how Monte Carlo tree search is developed, which is developed for unconstrained problems. It expects to just have the reward signal. It doesn't have any other additional constraints applied to it. So we're going to do something similar to what we originally did, is we're going to transform the problem into a version that does work with Monte Carlo tree search. And in fact, we're going to head into so what we're going to do is we're going to define a new reward. And this reward looks a little bit complicated, but it actually is deceptively simple once it's written down. What's happening here is we're going to say the system only gets reward if we're inside the set of safe beliefs. If it's outside, it gets 0. And then we're going to add this R0 term, which is defined such that is constructed so that any set that is, or any trajectory that is safe is guaranteed to have higher reward than any trajectory with a single time step that is unsafe. And that's what this ratio is doing here using our horizon. And the reason for that is we want a separation between safe and unsafe trajectories in terms of reward, so that convergence of our tree to maximum reward or maximum value as we sum them up guarantees convergence to safety, assuming a safe trajectory exists. So that's what this R0 is doing. And then after we've established safety, we're going to still ask that we are the most effective at gathering information as possible. And with this construction, we have a theorem that says that if the original problem was feasible, by that I mean if there existed a trajectory that satisfied the safety constraint, then the optimal policy of this transform version is going to be admissible and optimal on the original constrained problem, which was the one on the previous slide. So if there exists a solution to this, solving this reformulated problem is the same thing as solving that original problem, which is great because our tree can solve this problem. It can't solve the original one. There's just one little still here, which is how do we evaluate this indicator function here? It's a bit messy. It's we're saying, is this belief inside the set of safe beliefs or not? Since that is an infinite size set, we can't just look at it and say, well, yes, it matches. We need to have some way of evaluating this. And you may have guessed, given that we were already using sampling-based approximations, but we're going to do that again. We're going to see, can we just use some numerical simulation that approximates and converges to the true answer, yes, safe or not, but do so conservatively. So we can sample safety. That's no problem because we can just draw a point from the belief distribution at random using the weighting of the probability density. And we can do that m times and create a sample average and a sample standard deviation. The question is how many points do we need to sample before we're confident that we have achieved at least alpha safety, say 90%, for example. And luckily, there exists literature that tells us what a conservative bound on this is. It's a conservative version of the Chebyshev inequality. It just looks weird because it's using finite samples. But when these conditions are satisfied and we can design our algorithms so they always will be, or so that we are at least always satisfying m is greater than 2, and then we can just require an additional level of conservative on the rest of the conditions. We can then say meeting this guarantees that we are at least alpha safe. It's conservative, so we'll probably be safer than required, but that's okay. We always are interested in putting in margins in aerospace anyway, so we'll do this. Visually, what this all represents is that what I was saying before, we've now made it in a computational tractable way that any trajectory that is safe is guaranteed to have a higher value when we sum all the rewards up than any trajectory that is unsafe, because the unsafe one loses all of its reward here, whereas the safe one keeps some minimum level plus some information gathering return. So this is great. This allows us to perform safe fault estimation, and we can validate this in our simulations. Before we go into that, I want to talk a bit about our baselines. Or actually, before I go into that, I should pause and ask if there's any like questions about the theory and stuff I've just, because I know I've been talking about that for a half hour. So if anyone has any confusion or on what we're trying to do, feel free to let me know. Otherwise, I'll show you how it works in simulation. Whichever, if it'd help you understand the presentation, feel free to ask them now, or we can do it at the end. Okay, yes, that's a great. So he was asking at the very beginning. Let me see. Can I see all slides? When we were talking about when we had degradation and bias terms, how do we define those? This is at an abstract level, so this isn't for a particular system in mind. It's actually most closely modeled for our spacecraft simulator, which I'll show you a video of in a few minutes. But the idea is that for this level of abstraction, what we're saying is that it's a value between 0 and 1 for every actuator. And if it's at like say 0.6, that means if you command give me 1 unit of thrust, you actually get 0.6 units of thrust. So it's just, or sorry, you get 0.4 units of thrust because you're 60% degraded. So it's a linear map between expected and actual performance. Now, is that the most realistic model? We could definitely quibble on that for sure. But the nice thing is you could put in a higher fidelity model here if you want. This is just the one we've adopted. And it's the same thing for this bias. It's a simple 0 to 1 map of how much of a full input is being constantly put into your system. So I'm thinking for this in terms of thrusters is where all of this is coming from. But it's not, you could always do other types of actuators. Like you could have actuators that are allowed to go negative, for example. We're just assuming like something that's either off or on, and there's a range of values. So that's where this model is coming from. Is thrusters is what I'd say always think about that. Yeah. And then similarly for the sensors, this one's definitely a little bit more contrived because we didn't focus on accurate sensor models in this case, just like functional ones. But it was doing the same sort of thing, is that we set a maximum bias level and then said the sensor is either between 0 or 1 of that maximum bias. It's just a constant offset that's being put in, kind of to represent the idea of a calibration error that you haven't caught or something like that. Like maybe some maneuver ended up leaving your sensor just like a little askew. It's kind of the idea. The degradation of the sensors would also be just like kind of mapping a calibration error that like you should be measuring like a 2 meter displacement, but you only measure like a 1.5 on your IMU, something like that. Mm-hmm. Oh, good question. Yeah, you could handle this different sample rates. You'd have to do some sort of like filter that is okay with asynchronous updates. And when when I get to hardware, I'll talk a little bit how we did that. But maybe one thing you could do is you could set your time step to be the smallest sample rate that you care about, and then just not provide updates. And you could adjust this model so that you're not expecting to see an update on like odd number time steps, for example, from some of the sensors or things like that. That could be incorporated in pretty cleanly, because all we really need this like Y can be replaced by it could be replaced by a nonlinear like sensor model or asynchronous sensor model, as long as we do need at some point discrete measurements, but if you could represent it as a discrete measurement, for example, like another way you could do is like integrate like 10 samples and then just say that's my update. That would also work, as long as there's like time steps where because the time steps don't have to correspond to when you get the information, they just have to correspond to when you make a decision. So as long as you can define decision times, you can handle that. Yeah.
Oh, sorry.
Yeah. Sorry.
Yeah, so like different sensors and actuators have different sample rates and also like control cycles. So I'm just curious as to how that maybe like when you go to the hardware example,
Yeah.
it'd be more evident.
I don't have in great detail, so I'll just answer it now. And there is that we would basically what we did is we would run our estimator in the background, and then when we got to the next decision step, we'd say this is the belief at
Got it.
that at this decision step. And the way we'd model it is we would model all of that information just being processed instead of one observation. You could think of like instead of like a single observation, you can think of it as like an observation update.
Mhm.
So when we get to, let me go to the tree diagram. Let me just see all slides. So like using this diagram. So instead of this being like a single sensor observation or all your sensors reporting, you could think of it as just the information that was given by all those sensors across the time window. Like I'm thinking now like information filtering is if you processed it all and just handed it as an innovation update.
Got it. And
so-
I guess that alludes to my last question, so I don't want to take too much time, but you're representing that you mentioned like particles and these particle updates on each different node, but what are these particles representing? Is it the sensor
Okay,
readings or is it?
yeah. So this is the baseline we're comparing with, but then we also you can also sort of think of what we're doing as particles, and each particle is supposed to represent the total state of the system. And when I say state, I mean physical state and fault state, all wrapped into one. So when we go to this diagram, what's happening? So the baseline way of modeling it would be a particle that just has a lawn vector with physical states, fault states. It's highly dimensional, but it's one point in this highly dimensional space. And then what we do in our method, our innovation, is it's one point in fault space and an entire distribution in physical space is like considered as like a particle. So these particles represent possible faults with different weightings, and then corresponding dependent
Oh, interesting.
physical state, like what you would expect the belief to be if that was the true underlying fault.
Got it. So each state each particle represents a state in your system, including the fault states, and then that has just a probability distribution for each state, and then you try to maximize the probability for what the next state would be.
Yes, because the predicted state that best matches what we've seen is most likely to be the true fault, because each of these faults has a distribution on physical state, means we can make a prediction on the distribution of the observations, and we use that to compute a relative likelihood. And that's in fact actually what's going on in this equation that I sort of glossed over. We have this Bayesian update, and the more likely an observation was given an underlying fault, the higher it'll be weighted on the next in the next level of the tree or the next level of the simulation. And that's how we're converging. It's exactly what you're saying.
And then at each time step in real time, are you running this Monte Carlo tree-based Monte Carlo search?
Yes.
Okay.
The time scales are about like a second to 2 seconds or so. So we're trying to run this like all in a second or two, which is one of the challenges, is getting this all to run fast.
Yeah, I was wondering I was gonna wait for the the
Yeah.
hardware aspect, but the computational efficiency, it seems like
Yeah, well, I'll defer that towards the
Okay,
end,
thank
but
you.
that is a good question. Anything else or from online? Otherwise, I'll go into simulation results. I think thank you for the questions. I think that was good things to clarify. Gonna start heading there now. All right. So to simulation validation, and let's see, how am I doing on time? Well, we'll go into extensions as we have time for them. So the baselines we were comparing with, we're thinking of these like different levels of capability, which is to think over a horizon or over a single time step of like, what should I do next, but no thought for the future. Thinking about deterministic models, which can't really capture this, like it might be this or it might be that, but they can only say the dynamics are this, and they will evolve in a specific way. Versus probabilistic models, which is similar to ours, where we have these weighting on different possibilities and a different like a probabilistic representation of how we propagate this state of the system. So the first baseline we're comparing with is control barrier functions, which are not intended for fault estimation. They're just a way to ensure safety in robotic systems. And the idea is they define a safe set as everywhere where the safety constraints are satisfied. And the closer you get to the edge of the safe set, the stronger the restoring signal is to push you back into the safe set. They're a very like minimally invasive way of ensuring safety, but they assume a deterministic accurate dynamics model. And as we'll see in our simulations, this breaks down when you don't know what the fault state is, and therefore they can't ensure safety. The other one we did of a deterministic model that plans over a horizon is sequential convex programming. The way that works is it convexifies all the safety constraints at a specific time step and tries to plot a locally safe trajectory at each time step, and then redoes this for each time step. So you get a non-convex but feasible trajectory that you're trying to steer your system to. And then again, that works great when you have a deterministic model. You can do some really powerful things with it. But when there's uncertainty over the actual dynamics of your system, this starts to break down because the feasible trajectory you have might not be feasible because it's assuming dynamics that might be incorrect. Looking at the probabilistic models, we thought about a greedy solver that uses all this information, uses our marginal filter that we've given it, but only thinks to one time step. It doesn't look into the future to see if there's going to be a collision. It just says, am I safe on the next time step? Great, maximize the information we get. And as you might expect, this is going to work poorly when we care about safety. And then the last one is ourselves, which does all of this and plans over a horizon. And for one more baseline, we also tossed in a random solver that considers none of this. It just fires at actuators and sees what happens. So perhaps unsurprisingly, or otherwise I wouldn't be sharing the results with you, we outperform our baselines. And in particular, we outperform those greedy and random solvers because they're destabilizing the system. So to start with, our baseline cases, we're doing fault diagnosis when there's binary failure. So either things are working or they are not. And they're in proximity, so about 10 meters away from an obstacle. So the things to note here is that every one of our SV solvers is pretty good at finding the underlying fault and converging to it quickly. There isn't really a significant difference with the level of planning. And maybe surprisingly, the random and greedy solvers are actually good at that too, because they're exciting the system. They're injecting new they're injecting new actions into the system, which gives us new information, and that lets us learn about what's going on underneath, like what the underlying fault is on the system, because we can distinguish between these otherwise similar cases that are ambiguous until we try to control and do something. And that's why the control barrier function and the SCP are getting almost no reward, because they're not doing anything because they don't need to ensure safety, which is good in this case, but we'll show in the next simulation why that's a problem.
Sorry,
But
what's the x-axis?
Shoot, I got that cut off. That's simulation time steps.
Got it.
So which are they've been scaled to 1 second in this case, but you could always scale appropriately for your system. Thank you for that. That was what I missed last night when I was editing. Sorry, so these all gather information, but as I kind of alluded to on the previous slide, the random and greedy solvers pay the price by destabilizing the system. The actions they take to learn about the system might send us into the obstacle, or we also restricted these systems to stay within we wanted them to not venture too far away from the initial conditions, because that would also indicate some sort of instability. We're starting to fly off in an unplanned direction. So one of those two things are happening, and the greedy and random solvers are now giving us very little safety by the end of the experiment.
Excuse me. What can you go back a slide?
Of course.
What color is the S-feast algorithm on those charts? It doesn't appear to be showing up in the legend.
The colors are, thank you for asking. I forgot to mention this. S-feast are the blue, purple through orange. The brighter the color, the more planning that S-feast is using. That's
Gotcha.
what that's supposed to run.
Okay.
No, thank you for asking. I'm supposed to mention that because without the image caption, there's no way to know. The next scenario we looked at is this similar idea of being near an obstacle, not on a collision course, just nearby. But now we have random biases and degradations. And the interesting trend to note here is that we're now gaining information passively as the greedy and control barrier functions, because these biases are themselves injecting information into the system because they're uncommanded control inputs. So that gives us information about what's going on, but we intentionally made these biases ambiguous because for the same amounts of bias, there was multiple degradations also occurring, which meant that unless you actively sought to break this ambiguity, you would still, these CBF and SCP algorithms wouldn't get further information. They wouldn't get as much information as S-feast or active baselines of random and greedy. And that's why they saturate out a little bit lower. And the other trend to see here is they get some information immediately from the biases, but they get a little bit more information as the experiment goes on up until this point, which I'll explain in a second. And that actually corresponds to when the CBF and SCP algorithms are trying and failing to maintain safety because they're approaching the obstacle or approaching the bounds of the experiment. And at that point, they need to do something to maintain safety. So they try a control action that they think will ensure safety. But because they didn't gather enough information about the degradations present in the system, they're failing to gain safety. So they're still crashing, but they're gaining a little bit of information, too little, too late. And that's what these rises are here. This slight drop off of the control barrier function is actually due to the filter going unstable. So it's turning, so we penalize it for doing that. The reason is that control barrier functions, being a simple method that isn't very invasive in your system, expect to be able to command unrestricted control input, which isn't always physical. So they might command something that exceeds our actuator limits, and that can cause divergence of the filter. But so our baselines aren't working, but SFeast is still maintaining safety, and we're starting to see that the higher levels of planning are doing a better job of maintaining safety. This becomes dramatic when we start to consider those motivating examples of being on a collision course with our obstacle, where we're now approaching with 1 meter a second. So we're going to hit in 10 seconds if we don't do anything, these obstacles. So we call this an adversarial failure because this is hard to solve without planning. The reason for that is any of our single step algorithms are not going to be able to reliably determine that the solution is to reorient, then slow down, because these thrusters don't work, which means that our random and greedy approaches drop very fast. Keep right clicking. And our control barrier function and SCP are also failing because they're not getting information about the system and they're not seeing the actions. They're not understanding the state of the system until it's too late. And again, they're starting to crash into the obstacle. The similar trend occurs when we are doing this with degradations and biases. We see kind of what we saw before, that there's some information given to our baselines, but not enough. They try to maintain safety and get more information while doing so, but do so too little, too late. And across both of these, we see that the level of planning provided to SFeast increases uniformly or monotonically, not uniformly, the level of safety that's being achieved, because with more planning, we're seeing further into the future and we're getting a better understanding of what actions are reliably leading us to safety and which actions are potentially dangerous, which I think is a great, exciting result. I really like seeing this like straight increase with levels of planning. But we don't have to stop here. We can also take it to hardware. My lab, the aerospace autonomous robotics and controls lab, we rebranded recently at Caltech, has these flat floor motion simulators, which gives us the ability to replicate some of the dynamics of spacecraft, most noticeably the near frictionless environment, which is part of the challenge with this type of fault estimation, because you can't just hit the brakes. You have to actively put in a control thrust to avoid collisions. And this mimics that quite well. So we have these flat floor 3 degree of freedom spacecraft, because they can translate into axes and rotate. And they look kind of like this when they're just floating around, giving random control inputs. This is actually the one we used for our experiments, and I'll show you a video of it working in a second. The way these spacecraft simulators are set up is they have air bearings on the bottom that's fed with compressed air at like about 100 psi. This creates a cushion of air, kind of like a reverse air hockey table. So it's near frictionless. It's not perfect, but it's sensitive enough that if you don't clean the floor with a Swiffer off before running experiments, you'll see a noticeable difference, which is another fun fact. We have versions that can have a linear actuator to simulate the Z direction. That's not used in this experiment because it's complexity than was necessary to demonstrate the capability we're trying to show. Similarly, you can also add an attitude stage that has a spherical air bearing, so it can rotate in the other 2 axes as well. Again, we don't use that for our paper because it's easier to visualize and represent what's going on when it's only 3 degrees of freedom, but it's a capability we have. And then the top stages have thrusters that provide redundant actuation in each axis. So that allows us to both command translation motion, but also command a torque if needed. And that we've used this isn't my work. This is work that was done before I joined the lab, but we've used this for all sorts of experiments. For online, if these videos aren't coming in, they're on our lab's YouTube channel if you're interested. I don't know how well Zoom will show this off the library's Wi-Fi, but we can use this for like multi-agent experiments such as docking, or for experiments with collision with comets, like I'll show you in my work on the next slide, but I'll let this play out. So autonomously rendezvous, dock, and make physical connection right now. There it is. So it's a fun spot to play with. We can do a lot of different types of experiments and kind of make this a bit more real. So in our case, we stayed in the single agent to match all of our simulations I just showed you. Skip around a bit because you've seen a decent amount of this through the talk. These are the subtitles if you're watching without any prior knowledge to my work, but I'll narrate over these instead to try to emphasize the things that I think are interesting for this talk today. But what's happening here is we're just on a collision course and we're running one of our baselines, the control barrier function, which again doesn't try to stop it until it's getting too late because it's a minimally invasive method and it ends up running into the obstacle. We're doing the same sort of thing in simulations where we represent the keep out regions in red and we tell it to avoid with high probability, in this case 90%, collision. We want to be confident in our belief that we're not going to run into this the obstacle. And then we're updating the same sort of representation I showed you before, where we have these component health are estimated as red or green. Obviously green being it's working and we're confident about that, and red being it's failed and we're confident that it has failed. When it's a white color, that means we're not really sure what the status is of all of these. And we have the squares are representing these actuators and the circles are just abstract representations of the sensing. In this case, we're not doing onboard sensing. We're using Vicons and simulating the sensors when we pass the information to it, which kind of goes to your question of we integrate all that Vicon data and just give it as a like single information update plus degradations and biases. So now it has a belief on where it is, but it's still running the control barrier function. This is actually the same video as you saw in the opening. So it's crashing and then the filters are diverging and everything's breaking. When we run Feast without safety, we do start to take actions, and we will gather enough information to know what the correct fault is. We've identified those thrusters don't work, but we sent ourselves into this comet. So we need to be proactive about both identifying what's wrong with the system and avoiding the obstacle. So when we're running our method, again, same thing. The retro thrusters are the broken components. That's the true fault. What SFeast does is it first takes actions to that will not increase the risk. So it's going to accelerate to the side. It doesn't add energy towards the obstacles. And that gives it enough time to start realizing that those work, and it should suspect the other thrusters. It should reorient, and it should slow down to avoid collision. So this is running in real time on the hardware. It is running with a somewhat low level of planning. This was about somewhere between 80 to 100 simulations per time step, which was about 1.3 seconds. And I don't know if you recall from the previous slide, but we wanted to run more like 200 or so to like have a high chance of success. So this doesn't work quite at the 90% level, but it does still give us safety a lot above our baselines. And it indicates that the faster we can get this running, the better. But running in real time is one of the challenges. And it's actually the thing I'm starting to work on now in my PhD. Don't have slides on it yet because we're still in figuring out the code implementation. But the nice property about SFeast is that increase in performance with increase in computation. So you can get the more performance you can throw at it, the better it tends to work. And we've seen this in our simulations. So summary on SFeast is that we can identify a number of faults across different situations and scenarios, and we can provide theoretical guarantees of convergence, and that the way we're approaching this is well motivated, and we can run in real time on the realistic hardware with the option to improve our performance as we improve compute power. And we can extend to systems with tractable Bayesian updates and constraints, including the extensions that I'll get to, but I'm going to defer to Ken if we have time for that. Should I go through, how much more time should I talk for? Or should we just go to Q&A? All right, I'll aim for about 10 minutes or so extension. So some of the other things we've taken this approach and moved towards, basically going back to our original flow diagram, the questions we have are, all right, it works with spacecraft, it works with these like systems, you might even say that are pretty nice. They have redundant control actuations, they have redundant sensors. We'd like to build redundancy into our spacecraft systems. Does it work on things that are maybe drastically different? So, and can we extend beyond just faults and think about other types of things we might want to gather information about that are going wrong with our system? And the answer is yes, we've done some preliminary work on both of those questions, and we've seen promising results. So one system we tried extending this to is tracked vehicles, for example, a PackBot system. This was in support of a DARPA project, which is why we're using PackBots. But the things that are dramatically different about this system is that it has 2 tracks, which can each have degraded performance, and up to 3 cameras for a visual inertial odometry, which is a machine vision way of navigating. And the important part about that for our context is that a failure mode our team was seeing with the VIO sensors is that if they failed to initialize or find a landmark that they could track from one scene to the next, the cameras wouldn't raise an error, but they would like grab onto artifacts which weren't giving it good information. So we start to see a drift coming from the VIO because it's just injecting random walk noise into the system, which is undesirable, but it's also pretty different from the types of faults we were looking at before. So we decided, see, can we model this and can we reliably identify it? So in this experiment, what's going on is that camera 1 has this drift error, but we've currently told it that camera 1 is working and it must trust it. So as we propagate this tracked system in simulation, it's going to drive around trying to figure out what's wrong with itself, but this drift term is growing without bound. And at this point, we've have an entire, like, I think we have 2 full revolutions of like drift has been put into the system. It thinks it's way over here where it's actually over here. And there's just really no correlation between the real system and the estimated system. Those things are going poorly is how I describe it. Now, when we allow it to know that camera one is failed, it's one of the possibilities it can suspect. It's going to drive around and it's still going to see this large drift. These hash marks you're seeing are saying that it's disabling one of the cameras to see if it fixes the problem or not. So it currently suspects these two. It tries turning them off. That doesn't work. We're starting to see bifurcation in the belief, some pretty nonlinear behavior happening. But it eventually tries turning off camera one and it starts to get good initialization and can identify that camera one is in fact the problem and one of its tracks is degraded and it's working, which is great. That was this was kind of our first stab at applying to a new system. And we were happy to see that the ideas do translate pretty well, as long as we can provide a model for the fault, which is a restriction. But one thing we could do in the future perhaps is try to learn the models and then give that to SFeast as its as the fault model and just match with potentially learned information in the future. We then also were like, well, can we, if it's working for finding the faults, can it work to do safety at the same time? Because one of the parts of the DARPA project is they wanted to drive along this narrow track here and inject faults without collision. So this is, again, pretty different. We have the same fault as the last example, but now we have this corridor that it has to remain within, which is, again, pretty different from how our spacecraft work, because we can turn off we can stop the robot, we can move it around, but we don't have as much space before we have collisions. So when we turn, when the safety is off, so we're just running feast and not paying attention to the obstacles, we do run into, we go out of bounds pretty quickly, which is to be expected because we're just gathering information with no concern for where we head. But we do eventually converge to the correct fault. So that's promising. When we start to think about these safety constraints, we turn safety on. We start to see that it's taking smaller and more conservative control inputs to try to figure out what's going on with it. The VIO drift is starting to occur, and it's getting very out of like very off from the ground truth of the system. But it is eventually able to realize that camera one might be the problem. We've ruled out everything else. Turn that off, reinitialize, and now we can start shuffling back and forth to test out what's going on with our drive on each of these tracks and eventually converge to the true correct fault without violating any safety constraints. And we do this, again, all autonomously, just by planning with SFeast. And we're actually at fairly small levels of planning, I think up to 400 simulations per time step. And we were seeing a pretty good, this doesn't show up super well on the projector, but we're seeing a pretty good separation with increased planning beyond a minimum. I think n equals 20 was doing worse than the random action, probably because it had explored too little and it was stuck on a random minimum. But once we get enough levels of planning, we're seeing increased performance with experiment time step, which is what we expect to see. The other thing we extended this to, this was presented last month at the IAC, was can we use this idea of active fault estimation to try to identify not just a fault, but somebody who's attacking us. So the motivation on this was that we might have a distributed system. Sorry, this got washed out, but there's a asteroid here, comet, or some small solar system body that these spacecraft are working together to observe for a science objective. And they're measuring the body, they're measuring each other, and they're sharing that information with each other to perform belief updates and come to a consensus as a group. So the question we had is, what happens if one of these agents is compromised and is working against us? Maybe because somebody backdoored it in when it was being assembled, maybe it was hacked after it got deployed. We don't really care about how it got control, but it is an area of increasing concern, is that we will run into rogue spacecraft that are controlled by somebody who isn't the person who launched or is supposed to be operating it. And they could be putting us in an unsafe space. And even more concerningly, they could be lying to us about what they're doing. They could be giving us false observations and trying to disrupt our consensus and our cooperation. So what can we do about that? Before I get to that, the reason why we were interested in this is because I think you've probably heard a lot about the promises of multi-agent missions, such as increased flexibility, increased robustness, maybe smaller spacecraft, so we get cost savings. So, but as I was saying before, there's a concern that as we have more stuff up there, there's more vulnerability. The attack surface is wider. So this is a problem we're going to have to deal with in the coming future. But we want them because we want these multi-agent missions because they enable things that are completely new that monolithic missions can't do, such as this was a project I did earlier in my thesis where we were doing 3D radar tomography by taking a full scan of Earth's vegetation in a single pass. But you can only do that when you have an extra axis from having multiple spacecraft. Otherwise, you can only get a 2D image. So we want this, but we also need to think about what could an attack mean to our system. So we set this up as a toy example where we have a group of spacecraft trying to maintain their formation. And from the defender, they're trying to just minimize disruption. We used an LQR cost just to give us our simplest system possible and see what we can get from that setup. Detecting attacks allows us to recover. So we defined a probabilistic metric called the Wasserstein 2 distance between the belief we expected to see and the belief we actually got. That's going back to the S-feasts using the update based on the information difference between what we predicted and what we actually saw. Just like that gave us information about the faults, this gives us information about whether somebody might be attacking us. Set that to alpha. Now different from safety, this is alpha stealthiness instead of alpha safety. The attacker would like to do the opposite. They would like to disrupt us as much as possible. Maybe give us a system that looks like this, where now the spacecraft are wildly out of position compared to where the central defender thinks they are. They might be unsafe. They might be in danger, but this might be very easy to detect, show that like some sort of chaos is happening. So we told the attacker that if you're detected, you lose. But to avoid it just going, well, I don't want to do anything, then we said, if you're detected with a probability above beta, you're in trouble. So we've set this up in a very similar way to our safety constraints with S-feast. We now have probabilistic constraints on detection. And that allows us to now define a 2-player game using Monte Carlo tree search. So now instead of green and red for faults, we have bright colors, which means attack input, and a dark color, which means, bright color, which means that high disruption from the attacker, and a dark color, which means minimal disruption. So the difference here is that both the attacker and the defender get a choice, and they would like to steer the tree, doing this exploitation versus exploration trade-off, towards outcomes that are good for them. So as the defender, we have to consider the fact that if we were to go over to, say, like this attack, which can eventually lead to a good scenario, a dark color, the attacker is never going to go that direction. They're always going to go towards the areas of highest value for them. So we have to steer towards areas that limit the attacker's options. Basically, what we want to do is force the attacker to either reveal themselves and lose, or not be able to disrupt us much. So that's what this tree is going to look like, is this kind of like steering towards something that is least bad from the perspective of the defender, or most bad from the perspective of the attacker. And we ran this in simulations. First, what we did was we ran with no attacks just to see what the stealth metrics look like and our false alarm rate. We decided we wanted about a 5% false alarm rate over the 20 time steps of the simulation, which corresponded to about 3 standard deviations. When we do that and we run with random policies, we get behavior that kind of looks like this. So the attacker is currently not paying attention to stealthiness. It's just doing random attacks. So it's actually causing a pretty big disruption. It's pretty far out of position, but as soon as one of these other agents looks at it and sees it really far out of position, it's detected, as we expect because of this metric. So we see that when the attacker is random, it's found very quickly. And this leads to a slow transformed reward, where this transformed reward is transformed just the same way we did with S-feast. We've given a base reward. All these rewards are going to the attacker now. We've given a base reward to the attacker if it stays stealthy. It loses it all if it's detected, and it gains more reward for disrupting the system while maintaining its stealthiness. So we see as soon as we give the attacker some planning, it maintains its stealthiness quite a bit better than than the random attacker. It can't be quite as stealthy as the unattacked system because this is indicating that our alarm threshold is working. It will eventually find the attacker, and the attacker is accepting that because it has a probability of being detected, not an absolute can never be found. But it's managing to balance these ideas of disrupting our system and remaining stealthy against a random defender. So what happens when the defender is planned, if we are using this planning on the defender? We see that we think because it's a two-player game that with the increase of planning, we don't see a lot of difference until we get to shoot, I have a background that isn't white, but the projector is still a bit of a brighter color than I was hoping for. Well, you're just gonna have to take my word for it that once we get to n equals 2000, the dot for the stealthiness has a consistent gap. It's consistently revealing the attacker more often than the random play, and it's doing that throughout the entire experiment. It kind of goes like along here. So it's not a massive gap, but it is persistent. It is showing that sufficiently high levels of planning. You'll notice it's much higher than SVs now because we have two players that are interacting here. Does give us a persistent advantage and allows us to limit the capability of the attacker, force it to reveal itself, or force it to not disrupt our system, which is what we care about. And when we play that out in simulation, we see that the attacker can't really deviate as far from its initial position as it wanted to because it needs to maintain stealthiness. And if it does start to deviate, it is caught pretty quickly out of position, even though because this is, I forgot to mention this, but because this is an angles only navigation problem. So it isn't seen like it's trying to take advantage of the fact that there's unobservability. Like for example, this observation is stealthy because a long line of sight it looks to be in position, but it can't do that in all directions if it wanders too far out of position. So that's what we're showing in this simulation. And we're showing that we can, again, take this idea of actively seeking things out, in this case, looking for things that don't match that could indicate an attack. And we can use that to add robustness to the system beyond what you would have through, in this case, random play, or in the case of faults, passive estimation. And again, this is ongoing work, so we're just showing initial proof of concept. So at this point, I'd like to acknowledge my collaborators, everybody else who's helped me with this project, and all of our sponsors, and then end on the summary that active sensing provides a powerful framework for gathering information about parametric uncertainty within your system. SVs can be adapted to these systems to give a tractable and interpretable method for planning and optimal information gathering. And then we can extend that to other systems and other types of faults or things we'd like to gather information on. And then my plug, which because it's a core part of my research, is that tree searches are great for real-time performance and increasing performance with computational resources, which I think is a very natural way to look at it when we're in a domain where our resource allocation is constantly changing. So with that, happy to do more questions, and I'll stick around for a little bit for people in the room, but we can do like 10 or 20 minutes questions online. And you can also just reach out to me at my email if you'd like more information or if you would like a copy of any of these papers.
Wonderful, wonderful presentation. That's very exciting. So let's see any question here first from here. How about online? Okay, 1 second. Somebody has a question. Let me enable your mic. One second. Allow to talk. Okay, so
hello. Thank
go
you very
ahead.
much for the wonderful presentation. It was very interesting. I just
Uh,
was if,
1 second. Could you say a few words about you? What's your name?
my name is Alexei. I'm a PhD candidate at Worcester Polytechnic Institute in Massachusetts. And I wanted to ask if any kind of active fault estimation was ever used on a real mission right now or tested.
So you're saying like if there's any flight history of this type of idea?
Yeah, more in general, like just active fault estimation, not this particular idea. I saw your hardware testing, but just active fault estimation in any other
Great question. For space missions, not autonomously. There's definitely been diagnostic tests and things run, but this idea of like autonomously distinguishing between things on a spacecraft hasn't been done to my knowledge. And the main reason for that is because, as you probably can guess, space is pretty conservative. and autonomy is still, I'd say, a developing field for spacecraft. One of the reasons, however, that I think this is interesting, and I think we should start doing this, is because we're eventually going to want to run missions where there's no other way to handle faults but to do it autonomously. And I think that's an opportunity for researchers like myself, because if I come to somebody saying, hey, I want to like autonomously drive their spacecraft, the answer I usually hear is like, well, we don't trust it enough. And we spent X million billion dollars on this. So we don't really want to risk it on an algorithm that maybe isn't, we're not sure about. But if I tell you, well, will you let me take over when your spacecraft is doomed? Then usually, I imagine it's usually a little bit more open to using autonomy. And it is, I think, fault handling has been one of the few areas that autonomy's routinely used. But the current approach is to get into safe mode and do that autonomously, like safe the system, point home, and establish communication with the ground. And then we usually stop because once we've gotten communication with the ground, they can take over. But I'm thinking about missions where we'll just have to have more proactive autonomy. And that's because we have like the idea I had here is like time constraints such as docking or landing on something, or there's just too many spacecraft because we've got companies that are wanting to fly thousands, tens of thousands of spacecraft. At some point, you're not going to be able to staff enough people to deal with everything that goes wrong. You need to at least take the routine information gathering and just make it happen. But it's still emerging, at least to my knowledge. If anyone knows otherwise, I'd really like to have any information that I could then update my citations with.
Thank you very much. Thank you.
Thank you.
Yes, hi. I have a question. My name's Adrian. I'm just an independent researcher. Have you considered potential applications for something like autonomous robotic surgery, for example, utilizing this this type of technique?
Robotic surgery, you said?
Yeah, autonomous
Autonomous
robotic
robotic
surgery with the appropriate sensors and getting guidelines, whatever. But utilizing this concept.
I hadn't thought in that direction because for kind of the same reason of that's a very risk adverse domain, but I don't want to like rule it out of hand because I think one thing you could always do is for applications like that is, or one of the things I didn't talk about today, but I have in mind with this idea of like active information gathering is that this could be part of any autonomous systems, like just self-check of you don't need to be necessarily in a time critical situation or like in any imminent danger, but you could always do this sort of like active information gathering as just a way to verify your status. You know, I haven't seen any alarms, but I also haven't checked for spacecraft. I'd say like a couple months, maybe for surgery. It's like at the start of the day. It's like, can we just run through these tests, kind of autonomously think about things that might have gone wrong and debug that? So that might be a possibility. The only case I could think of doing it like while you're mid surgery is if for some reason there isn't a surgeon available and maybe it is time critical because your patient needs care. But I'm not familiar enough with the domain to like speak beyond that is the one thing. But I'd love to see it someday as long as we make sure we're very tested and validated.
I have a question. I guess introduce myself. My name is Attila. I'm a guidance navigation control engineer at Turion Space.
Okay.
The question I had, by the way, very great presentation.
Thank you.
I enjoyed it a lot. One question I had was, how would this be augmented and utilized for RPOD or rendezvous proximity operations and docking, specifically because you have a constraint in there, or sorry, an inequality constraint, such that I'm assuming you're setting that inequality constraint to check for the range of the object, and then you're discounting future trajectories and actuator commands so that you don't collide.
Mm-hmm.
But in docking, you technically are colliding with it up until the constraint of the equality of 0.
Yeah.
Versus reaching an equality of the reward function, or rather the cost function being a function of the distance.
Yeah, that's
so how
great.
would you kind of tackle that?
That's a great question. There's two aspects of that I would think of. There are two ways you could go about doing it. So one way you could go about doing it is treat this as like an emergency protocol that takes over, and then once it's found the fault and stabilized the system, it can hand back over to your nominal docking application.
So that's like one way to do it. That's probably the least invasive way. The other way you could do it is you could set constraints. So we could set constraints on things other than position. Like we could set constraints on velocity and things like that. And currently we haven't explored time varying constraints, but I don't see any reason why we couldn't. So you could have some sort of like envelope that's contracting to the conditions you need for docking, for example. And maybe that could be connected to your confidence. Like you don't try to go into docking until you're confident enough about the state of your system and its faults to approach. And we sort of have that like as an emergent behavior, in that as we gather more information, the uncertainty should shrink. So we can approach our constraints with more confidence that we won't violate them. So you get that a little bit, but you could probably augment that behavior by having explicitly time varying or just handling back to a nominal docking software.
Yeah, I think I completely agree. Like having some sort of a velocity constraint plus
Yeah.
a combination of the time varying constraints, is specifically like any degradation in your sensing. Like if you have loss in sensing and you have lower confidence in the next state, you might actually want to back out because something is causing that confidence in the next state in the docking procedure to be high.
Yeah.
The error to be high. So you might want to like reduce.
Yeah, and we can write directly without having to modify F-space at all. Any constraint you can write on the belief, we could apply like out of the box.
Right. Yeah. Which is good. The modularity in the constraints is like really important, I think. The other question I had was, have you looked into the back propagation? And in the step that you talked about, you have this like step where you're doing exploration versus exploitation, and you're doing back propagation to check other possibilities and like branches in your Monte Carlo tree.
Mhm.
But have you looked into if that back propagation is even necessary? Because it's kind of like a concept in terms of like chess algorithms where you have like a 2 to 3 sigma level confidence, and if the confidence in like if 2 3 if the choice of your branch, generally speaking, in your algorithm is mostly going to be the best solution, is it just good enough to just continue down that tree without having to backpropagate? If 99 or 95% of the time that's the best solution, that might actually save in your computational efficiency.
Yeah, let me go to the slide because I want to make sure.
But it really depends on like how many times you actually have to do the backpropagation, and that if that leads to a better solution.
Yeah, so this is the slide you're talking about, right?
Yes.
Can I get? All right, let me click forward. Oop, nope. Oh, that's why, because I'm going the wrong way. Let me get the key idea out of the way. So, yes. So if I'm understanding your question correctly, I may have failed to clarify this. This like selection, expansion, simulation, backpropagation is all happening in simulation. So this doesn't have anything to do with the realized step of stepping forward once you've made a decision. So you do this tree and you grow this entire tree before you take an action on the real system. This is all done in simulation. Then, so the backpropagation part of Monte Carlo tree search is to tell us how good the end of a simulated trajectory was. So what I mean by that is that while the robot's thinking, and this will take like a fraction of a second, but it'll think about where am I now? And if I do this action and I get this observation, then I'll do this action and maybe I'll get this observation, so on and so forth. Then it'll do that up to a maximum depth. And once it reaches that depth, it'll see what did I get? How good was all that information at the end of the day? And that's what's back propagated up. And then it'll repeat that train over and over.
Oh, okay. That's just for VNV, like verification validation, not necessarily.
No, that's how it does its part of it. Is it's thinking about this, and it does this like, 100, maybe thousands of times to think about that. That's what's being grown when we have, let me go to, I'll just go to our overview. That's what these trees are representing. These are all the possibilities it considered before it made a decision. And then it'll use that to make a decision. Now, once you make a decision, it's realized, right? And it becomes real. And we do the full information update from that decision. And we actually throw away the old tree. You don't have to throw away the old tree, We do so because there's so much branching that there isn't really much we save from the tree. And so you could potentially, it's something we thought about as an efficiency gain, is to use the real measurement as opposed to the simulated measurements to like seed the next tree in some way. And in some sense you do that because that updates your belief, and that belief becomes the root of the next tree to think about. But it is a question of like, could we use that information to maybe update the tree we planned on the previous time step so we can reuse more of it? And that is, I think, an open question with these types of Monte Carlo tree search planning. Some people are like, yeah, it's worth doing. And some people are like, you're just introducing like some bias or variance. You're doing a lot of work for not a lot of speed up, and just don't think about it. Currently, we just throw away the tree because it's just simpler to write the algorithm that way. But so to that point, there might be some use in back propagation. And then I think the other sort of thing you're talking about is like, could we use that information to update like our models or stuff like that? In one domain I could see this being done is if we're running SFeast on like a fleet of spacecraft, and like some of this, like we're seeing consistent like information that doesn't quite match. We could maybe, one thing I'd like to see, but I probably won't get around to it before I graduate, is like incorporating learning models. So like we learn a better description. This is our fault models as we run this. And we go, okay, we modeled it originally as like a percentage degradation of the thruster, but it doesn't really behave like that. Maybe it behaves more like a percentage degradation plus like there's some like residual bias term. I'm kind of like spitballing here, but so that's like some sort of back propagation in its own right, but that'd be to like a learning model.
Got it.
But we don't currently have that. That could be cool.
Cool. No, appreciate it. Yeah, that's all I had. Thank you.
Sure. So let's get you the microphone.
Hi, I'm an engineer at Millennium Space Systems, and I had a question about oh, my name's Daniel. Great talk, by the way.
Thank you.
I was wondering if the tree to solutions that are both like really good, like which one would it choose?
Oh, yeah. So it's possible that there'll be multiple actions that seem informative. With SFeast, the bias, it would, of course, rule out any of them if they're unsafe. But if there's two actions that look both good and look both to be safe, then and they're exactly the same, it'll select between them randomly.
Okay.
In practice, once you've run enough simulations, like one of them will look slightly better than the other because our reward functions are continuous. So there will always be one that's slightly preferred. But in the case of a tie, it would just draw randomly.
Okay. And another question was when you were showing the heat map with the different colors like the green and blue, and I was wondering what that represented exactly.
Sure. That may have been one I went to. Was it this one?
Yes.
Oh, yes. Sorry, I said that implicitly. This heat map underneath is where the current estimate of where it is
Okay.
in space, and the size of the spacecraft is exaggerated for this one, but you'll see that like it is usually pretty good, but depending on the information, it can get off into like the higher standard, which we would expect, right? It's not always going to be at the mean. It's going to be kind of scattered around. And there might be biases in this estimation depending on how accurate the fault model is. But it eventually has accurate fault and pretty accurate estimation. The reason why that distribution is so big is because we crank the noise up really high to show that we can still do estimation even when the noise is unrealistically high, which is, and then it gives me more time steps to like talk about while I flip through the slides. Sure.
While we're waiting for more questions online, we do have a question actually even before the event from our AIAA fellow or associate fellow, Mr. Michael Helton. I think I'll just give it to Jimmy. You can read it to the online audience.
Okay, so
because he said he apologized, he cannot attend the meeting, but he will watch the recording.
can this algorithm or system turn up faults prior to their occurrence? Like, so they say take the current situation with Starliner system, including their spacesuits. What faults can it find before they were known? Predictability is hard, but can be done. One risk is to get too entangled with the math process that would direct attention from more obvious faults. Can the system list those faults prior to their mission discovery from like the requirements or something like that? That's a good question and obviously a very valuable application. The current incarnation of SVs can't do that. It'd be something I'd be interested in being able to do, is some sort of predictive faults. The closest we can get to that is with the safety idea of let me go to this slide, where we have this idea that we don't know yet what any of the faults are, but we do know that depending on what they are, if it was the worst case fault, which case it is, we would be in danger. So what S can encode is the fact that we need to respond to these outlier faults before like something may have caused them to occur. So this is the idea of like, we don't know for sure. We have no idea right now that the retro thrusters are failed. But one of the first things we do is we start pushing to the side so that once we determine the retro thrusters are fault, we've already dodged enough that almost all of our trajectories are safe. So we can do that. And the extension to like undiscovered faults, that would have to go with these learning processes that I'd be interested in maybe incorporating if I had infinite time. One of the challenges for that is that it's an unknown problem, which is notoriously difficult. And we're sort of in the middle here where we have modeled faults that we've chosen that we care about, because that allows us to break apart some of the ambiguity between sensing and actuation faults. If you have a complete black box system, we started to explore this, but one of the initial things we found is if you have a complete black box between input and outputs, without assuming some structure of how your system like has its control inputs and how it has its like system outputs, there's a lot of ambiguity there, because a controls result is that for any input output system, there's infinitely many state space realizations. So we can't go completely black box because then we lose some of our diagnostic power. But there is I'd like to explore where those trade-offs are a little bit more. But yeah, for things that we totally have no prior knowledge of, you'd have to have some way of modeling the components of the system. So like maybe a digital twin, for example. And if the digital twin was good, we could maybe proactively look for faults on that. That might be possible. It's an interesting idea though. Yeah, any other ones, or we can end the webinar and just chat in the up to you.
Yeah, let me see if it's online. Online folks, any more question? Any question here? Mira? No? Daniel? I personally have some question, but I can ask him, afterwards, so I don't have to ask him while in the webinar.
Well, then I'd like to thank everyone for your attention, both in person and online, especially a Saturday morning. I'm glad people are interested in my research. And feel free, again, I'll put up my contact one more time, but feel free to reach out to me there, or there's all my backup slides, at my email or LinkedIn or however. If you come up with any more questions, I'd be happy to chat more. Yeah. Hope you all have a great weekend.
Yeah, thank you so much. Thank you, Jimmy. Wonderful presentation. Thank you so much. Appreciate it. Folks online, we are going to chat networking here. We'll stop the recording now.